Welcome to today's paper reading. Today's paper is titled, HuggingGPT, Solving AI Tasks with ChatGPT and Its Friends in Hugging Face. This paper was published at the 37th Conference on Neural Information Processing Systems, NeurIPS 2023, by Yongliang Shen and colleagues from Zhuang University and Microsoft Research Asia. The abstract highlights the challenge of solving complex AI tasks across different domains and modalities. It proposes that large language models, LLMs, can serve as controllers to manage existing AI models, using language as a universal interface. Specifically, the paper introduces HuggingGPT, which uses ChatGPT for task planning and selects models from Hugging Face to execute subtasks. This framework leverages ChatGPT's strong language capabilities and the extensive AI models available on Hugging Face to handle a variety of sophisticated AI tasks, contributing to the advancement of artificial general intelligence. Large language models, or LLMs, have shown remarkable performance in various natural language processing tasks. These models are pre-trained on massive text corpora and refined through reinforcement learning from human feedback. Despite their successes, LLMs face challenges such as being limited to text input and output, difficulty in scheduling complex tasks, and limitations in few-shot learning scenarios. To address these challenges, the concept of HuggingGPT is introduced. In HuggingGPT, the LLM acts as a controller that coordinates with external models, using language as a generic interface to manage and organize the cooperation of expert models. This approach allows LLMs to handle complex AI tasks by integrating multimodal capabilities and leveraging the strengths of task-specific models. Figure 1 illustrates the process of using a large language model, LLM, like ChatGPT to manage and coordinate various AI models from platforms such as Hugging Face to solve complex AI tasks. The LLM acts as a central controller, first planning a series of tasks based on user requests. It then selects appropriate expert models from Hugging Face to execute each task. Once the tasks are completed by the expert models, the LLM integrates the results and formulates a response to the user. This approach leverages the language understanding capabilities of the LLM to orchestrate a diverse array of AI models, enabling the system to handle a wide range of sophisticated tasks across different domains and modalities. Figure 2 provides an overview of the HuggingGPT system, which uses a large language model, LLM, like ChatGPT as the core controller. The workflow of HuggingGPT is divided into 4 key stages. First, in the task planning stage, the LLM analyzes the user's request and breaks it down into a list of tasks, determining the order in which they should be executed and any dependencies between them. Next, in the model selection stage, the LLM assigns the most suitable models from Hugging Face to each task based on the model's descriptions. The third stage, task execution, involves running these models on hybrid endpoints to perform the assigned tasks. Finally, in the response generation stage, the LLM integrates the results from all the models and generates a summary to respond to the user. This structured approach allows HuggingGPT to handle complex AI tasks efficiently. The capabilities of large language models, LLMs, such as GPT-3, GPT-4, PaLM, and Llama have been demonstrated in various tasks including zero-shot and few-shot learning, mathematical problem-solving, and common-sense reasoning. To extend LLMs beyond text generation, research has focused on 2 main branches. The first involves creating unified multimodal language models like Flamingo, which combines vision and language models, Blip2, which uses a Q-former to harmonize linguistic and visual semantics, and Cosmos 1, which integrates visual input into text sequences. The second branch explores integrating tools or models within LLMs, such as Toolformer, which introduces external API tags, Visual ChatGPT, which fuses visual foundation models with LLMs, and Visual Programming, which applies LLMs to visual objects using programming languages. HuggingGPT is an innovative system that leverages AI to facilitate collaboration among various models. It excels in integrating multiple models to handle complex tasks through a task-oriented dialogue system. Key features include support for multiple models, efficient task handling, and a user-friendly interface. This system finds applications in natural language processing, automating complex tasks, and enhancing user interaction. In the experiments of HuggingGPT, the system is designed to handle user requests through a series of stages. The first stage is task planning, where the system parses the user input to generate a list of tasks, manages dependencies between tasks, and generates necessary resources. The second stage is model selection, where the system selects the most appropriate model from a list of candidates based on the user request, and outputs the model ID along with the reason for the choice. The final stage is response generation, where the system answers the user's request directly, describes the process of task execution, and provides an analysis of the model's inference results. Table 1 provides an in-depth look at the prompt design used in HuggingGPT. This design includes several key features such as injectable slots like demonstrations and candidate models, which are dynamically replaced with relevant content before being processed by the language model. The task parsing template is structured around 4 main slots: task, ID, DP, and args, each serving a specific purpose in defining the tasks. Additionally, the system employs a unique symbol, resource task_ID, to manage resource dependencies, ensuring that tasks are executed in the correct order and with the necessary inputs. These elements collectively enhance the efficiency and accuracy of task planning and execution within HuggingGPT. HuggingGPT faces several limitations. Firstly, its planning heavily relies on the capability of the large language model, LLM, which means the generated plan may not always be feasible or optimal. This necessitates exploring ways to optimize the LLM to enhance its planning abilities. Secondly, efficiency is a challenge due to the need for multiple interactions with LLMs throughout the workflow, leading to increased time costs for generating responses. Lastly, the framework is constrained by token lengths, as the maximum token length is limited. This poses challenges in summarizing model descriptions effectively. Addressing these limitations is crucial for improving HuggingGPT's performance. Table 2 provides an evaluation framework for task planning across various task types within the HuggingGPT system. The table categorizes tasks into single, sequential, and graph types, each with specific examples and associated evaluation metrics. For instance, a single task might involve showing a funny image of a cat, measured by precision, recall, F1, and accuracy. A sequential task could be replacing a cat with a dog in an image, evaluated using precision, recall, F1, and edit distance. Lastly, a graph task example is determining which image is more semantically similar to another, assessed by precision, recall, F1, and GPT-4 score. This table is crucial for understanding how different task types are planned and evaluated within the system. Table 3 presents the evaluation metrics for single tasks, focusing on accuracy, ACC, and precision, PRE. The table includes data for models such as Alpaca 7b, Vicuna 7b, and GPT 3.5, showing their performance in terms of these metrics. Additionally, the F1 score is mentioned as a key metric for evaluating the model's performance in single tasks. The table highlights the importance of these metrics in assessing the accuracy and precision of task planning by large language models. Table 4 presents the evaluation metrics for the sequential task, focusing on edit distance, ED, and F1 score across different models. The data shows that Alpaca 7b has an ED of 22.27, while GPT 3.5 achieves an F1 score of 49.23. Additionally, Vicuna 7b's GPT-4 score is 18.66, indicating its performance in the sequential task evaluation. These metrics are crucial for assessing the planning capabilities of large language models and handling sequential tasks. Table 5 presents the evaluation metrics for the graph task, featuring LLMs such as Alpaca 7b, Vicuna 7b, GPT 3.5, and GPT-4. The key metrics used for evaluation include F1 score, F1, edit distance, ED, and accuracy, ACC. Notably, GPT 3.5 demonstrates significant planning capabilities in graph tasks, outperforming other open-source LLMs. This table underscores the importance of task planning in evaluating the capabilities of LLMs as controllers. Table 6 presents the evaluation results on the human annotated dataset, comparing the performance of different large language models, LLMs, in task planning. The data reveals that GPT 3.5 surpasses both Alpaca 7b and Vicuna 7b across various metrics, indicating its superior planning capabilities. GPT-4, being a more advanced model, demonstrates even better performance in task planning, aligning with the conclusions drawn from previous datasets. However, the table also highlights a significant gap between GPT-4's performance and human annotations, emphasizing the ongoing need for improvements in LLM planning capabilities. Table 7 evaluates task planning based on the variety of demonstrations, defined as the number of different task types included. The study reveals that enhancing the diversity of demonstrations can moderately boost the performance of large language models, LLMs, in task planning. This insight is derived from a series of ablation studies, which are detailed in the table, focusing on the impact of demonstration variety on LLM capabilities. Table 8 presents the results of human evaluation on various large language models, LLMs, focusing on three key metrics: passing rate, rationality, and success rate. These metrics are crucial for assessing the performance of LLMs in different stages of task planning and model selection. The passing rate and rationality metrics are reported in percentages, reflecting the model's ability to correctly interpret and execute tasks. Additionally, the success rate is a straightforward measure of whether the user's request is ultimately resolved. The data reveals that GPT 3.5 significantly outperforms open-source LLMs like Alpaca 13b and Vicuna 13b across these stages, indicating a strong alignment between objective and human evaluations. This performance underscores the necessity of a powerful LLM as a controller in autonomous agent frameworks. Figure 3 evaluates the impact of varying the number of demonstrations on task planning. The study reveals that while adding demonstrations can enhance model performance, this improvement plateaus after 4 demonstrations. This suggests a practical limit to the benefits of additional demonstrations in improving task planning capabilities. The HuggingGPT system is proposed to solve AI tasks using language as the interface. The system views an LLM as a controller that manages AI models from communities like Hugging Face. It leverages the LLM's understanding and reasoning capabilities to dissect user intent and decompose it into subtasks. Based on expert model descriptions, HuggingGPT assigns the most suitable models for each task and integrates their results to generate the final response. This approach demonstrates significant potential in solving complex AI tasks and opens a new pathway towards achieving artificial general intelligence. The authors acknowledge the significant support from the Hugging Face team, which has been instrumental in enhancing both the GitHub project and the web demo. Additionally, the contributions of individuals such as Bailey, Kaishan, Meiqichen, Qingyao, Yongliang, Zhuang, and Dingyao Yu in data labeling, as well as Wenqi Zhang, Wen Wang, and Ziki Tan in paper revision, are greatly appreciated. This work has been partially supported by the Fundamental Research Funds for the Central Universities, the Key Research and Development Program of Zhejiang Province, the National Key Research and Development Project of China, and the MOE Engineering Research Center of Digital Library. Thank you for watching.